Okay, let's start off with a couple of practice board questions. If a pilot plans to fly straight north when there's a 50-kilometer-an-hour wind from the west, in what direction must the pilot aim her plane to maintain the planned northerly flight if her plane has 140 kilometers an hour in still air? Okay, so there's a 50-kilometer-an-hour wind from the west. So it'd be like that. So she's going to have to aim into the wind. The wind will blow her this way, and then her resultant will be like that. That's how you draw the tip to tail. Okay, so this is her still airspeed. So this is 140 kilometers an hour. This is 50, and we want to know what her heading is. So we want to know what this angle is right here. So it would just be tan -1 opposite. Oh, not tan -1. Oh, look at that. Sorry, I jumped the gun there. So ka toa. So this is opposite and hypotenuse, so it's sine. So we have to sine -1 it. Ooh. So sine -1 of opposite over hypotenuse. And we end up getting 21 degrees. And that's northeast, southwest. So I'm not going north, I'm going 21 degrees west of north. So A is our correct answer. Okay, and our other practice question here. A swimmer tries to swim across a 200-meter wide river with 1.2 meters per second of current. Looks like it's going up. If he heads directly for the opposite bank, so he's not compensating, with an average speed of 1 meters per second, how far down the stream is the swimmer carried? So he travels here at 1 meter per second. The stream pushes him down that way, so he ends up downstream. Cool. So we want to know this distance here, how far downstream he goes, and we know that the speed of the current is 1.2 meters per second. So we just need a time. And if you remember, all time is the same in each one. So we have a speed for this and a distance for this. So if we use v equals d over t, move our t up top, move our v down below, like that. Our distance is 200 meters. Our speed is 1 meter per second. So it's going to take him 200 seconds. So that means he's going to be traveling downstream for 200 seconds. So again, if we use v equals d over t, move my t up top, this t is going to be 200 seconds as well. So I just have to go the speed, which is 1.2 times 200 seconds, and I end up getting 240 meters downstream. Okay, that's how you do those ones. So we are going to do lawnmower and sign questions, which is just a couple of specific 2D questions. They're not all lawnmowers and signs, but it just helps you identify the problems a little bit better. Okay, so you need to know the difference between navigation problems, which we did last lesson, and lawnmower problems. So with navigation problems, they're always given as an overhead view. So because of this, objects are allowed to move in 360 degrees. So this is an example here, right? The swimmer could go north, the swimmer could go west, the swimmer could go south, the swimmer could go east, the swimmer could go in any directions. But with lawnmower problems, they're different because they're given as a side view. So lawnmowers are only allowed to go forwards and backwards. They can't move up and down, so they can only move in one dimension here, just forwards or backwards. So that's kind of how you tell the difference between them. So we're going to jump right into an example. A 20-kilogram lawnmower is being pulled across the grass at a constant velocity. A force of 100 newtons is applied to the handle at an angle of 30 degrees from the horizontal. Find the force of friction and the normal force acting on the lawnmower. So we need to draw a free body diagram of this. That's the first thing we need to do because there's a whole bunch of forces acting on it. So our lawnmower is on the ground, and our lawnmower looks like this. So it says it's being pulled across the grass. with a force applied of 100 newtons. And it said that the angle from the horizontal, so this is the horizontal, is 30 degrees. So this is what our free body diagram looks like with that force applied in there. So there's other forces acting on this lawnmower. So we also know that there's a force of gravity. We also know that there's a force, actually I'm going to leave out the force normal for now. And we also know that, well, if it's pulled this way, then we have a force of friction. So I'm just going to leave out that force normal. There is a force normal, but I don't want to talk about it right now. So the lawnmower is being pushed or pulled at this angle here, but the lawnmower is not moving that way there. So what that means is that not all of this force is going into moving that lawnmower. So we have this, which we can call force applied in the x, and we have this, which we can call force applied in the y, right? So anytime you have something going at an angle, you have an x and a y, or two different components that make it up. So what we're doing is we're taking this and we can break it up into these. And the way that we can break it up into the x and the y is we can just use SOHCAHTOA. So we have an angle and we have a side. So this is adjacent and hypotenuse. So we can use CA. So co theta equals adjacent over hypotenuse. We want to find this adjacent side. So we move that up there. So if I go 100 co 30, I can find my adjacent side, which is my force applied in the x. And that's what I'm going to do. 100 co 30. And I get 86.6. Okay, so not all of that 100 Newton force goes into pulling it, so only 86.6 newtons actually goes into pulling it. But what we do know is we know it moves at a constant velocity, so we can use physics principle 0 if it's moving at a constant velocity. If it's moving at a constant velocity, my force of friction is equal to my force applied in the x. So we know that this is 86.6 newtons, so that's what my force of friction is. So we were able to find the force of friction acting on it. Okay. Normal force, the second part of this question, is a little bit different as well, right? I have this force applied in the y, so a little bit of this 100 newtons is pulling it up. So normally when we draw a free body diagram, we draw the forces from the center of the object. So I can take this force applied in the y, and I can move it over here. So I'm just moving this over here so it's part of our free body diagram, right? So if I have a force normal on this, well, I have a bunch of different forces acting on it, right? So I have my force normal here, but my force normal is not going to equal my force gravity because I have this extra force. So I can write out an F net equation. So F net is going to be, well, I have these two going up, so I have my force applied in the y going up, and I have my force normal going up, and then I have my force of gravity going down. So up is positive, down is negative for this. So if I want to find my force normal, this is my F net equation. But we know that the lawnmower is not moving up or down, so my F net is equal to 0. So all I have to do to solve this is I'll add an Fg and minus a force applied in the y to both sides. And I get force of gravity minus my force applied in the y. That's going to equal my force normal. Okay. So my force of gravity is just going to be mg. And my force applied in the y, well, I can use SOHCAHTOA to figure this out. That's going to be opposite and hypotenuse. So if I go sine theta equals opposite over hypotenuse, I want to find opposite. So I can go 100 sine of 30. And if I do that, 100 sine of 30 I get 50. Right, so this is 50 newtons. Okay, so mg minus 50 newtons is going to equal my force normal. So I just have to find this, and it says that my lawnmower is 20 kilograms times 9.81 meters per second squared. So I can solve that, and I can go 20 times 9.81. That's my mg. So if I take that 196, so I take that 196, and I subtract 50 from it, oops, don't need a bracket, then I end up getting that as my answer. And if I sort of draw out just a little free body diagram again, I have my force normal, which equals 146 newtons. I have my force applied in the y, which equals 50. And then I have my force of gravity, which equals 196 newtons. Well, that makes sense, right? This will cancel out with this, so I get a net force of 0. So let's try a board question. So pause the video and try this one on your own. So if the lawnmower has a mass of 12 kilograms and you pull it with a force of 50 newtons at an angle of 30 degrees, it accelerates at 1.2 meters per second squared. What is the force of friction acting on the lawnmower? Okay, so this one's a little bit different because it's accelerating, but our free body diagram is going to be pretty similar. So we have a force applied of 50 newtons. We have an angle of 30 degrees here. So within this is going to be a force applied in the x and a force applied in the y. And then we're going to have a force of friction, which is going to be smaller than our force applied in the x because it's accelerating. And if I wrote an F net equation, it's going to be force applied in the x minus my force of friction, right? And this is the only difference. Like when we were doing this stuff in 1D, it was force applied minus force of friction. Now it's force applied in the x. So to find that force applied in the x, I can use SOHCAHTOA. And it's adjacent and hypotenuse. So it's going to be co-theta is adjacent over hypotenuse. We want to find adjacent. So it's going to be 50 co-30 for that force applied in the x. Okay, we want to find force of friction. And we can break this so we can so we can subtract a force applied in the x from both sides. So we end up getting F net minus force applied in the x is equal to negative force of friction because that negative sticks around. So I'll just make this negative, this positive, and this positive to fix that. So this we can break down into MA. This we can break down into 50 co-30. And then that's going to equal our force of friction. So it said our lawnmower is 12 kilograms. So that should be outside of the brackets. And my acceleration is 1.2 meters per second squared plus 50 cos 30. And that's going to equal my force of friction. So if I type that all into my calculator, so I'm just going to go 12 times 1.2. Times it by -1, make sure it gets negative. Oops. I'm going to take that and times it by -1. So now it's negative. And then I'm going to add on that 50 co-30 onto there. Make sure my brackets are all good. So your force of friction is 28.9 newtons. And we have 2 sig dig, so actually 29 newtons would be a better answer. So the other types of questions that we're going to see are sign questions. And by sign, I mean like store sign. So preferably if you hang a sign in front of your store, you don't want it to move. So if something is not moving, then what's the net force acting on it? 0. What physics principle do we use? Well, we use physics principle number 0 if we have a net force of 0. When the net force is 0 and there's 3 forces acting on it, what should we always get? So this question is a little bit confusing, but if we think about it in terms of displacement, it makes a little bit more sense. So here's my house. Here's where I start the day. So say I go that direction, and then I go that direction. Well, if I want a displacement of 0 for the day, where should my last arrow go? Well, my last arrow should go back to my house, and then I go back to the start. So what we end up getting is we end up getting a triangle, right? And if I have 3 forces, so say, oops, let's try that again. So say I have a force going that way and a force going that way. Well, if I want a net force of 0, well, I have to go right back to where I started. Same idea. So now I have a net force of 0. So what you always get is you should always get a triangle. Oops, a triangle that starts where you finish. It's hard to write with my mouse. Starts where you, or that starts where you finish. Yeah, sure. Finishes where you start would probably be a better way of saying that. So triangle that finishes where you start. So it'll always be a triangle like that. And it'll always be a right angle triangle because those are a little bit easier. So let's do an example. So a sign is suspended by 2 wires as shown in the diagram. So draw a free body diagram. So I'm going to switch over here. I'm just going to draw out that sign because that gives me a little bit more room. So it's a 25 kilogram sign. And we had one cable going like that and another cable going like that. And it told us that there's 40 degrees and 50 degrees here. So if we draw a free body diagram, well, obviously we have a force of gravity downwards. And we also have force of tension from these cables. So force of tension can only go in the direction of the cable. So we're going to have force of tension 1 over here. And then we're going to have force of tension 2 over there. And that's what our free body diagram is going to look like. So the next thing asks us to draw a tip-to-tail vector addition showing the net force on the sign. Well, the sign isn't moving, so the net force is going to be 0. So if we draw this tip-to-tail, all I'm going to do is so my arrow looks like that right now. I'm going to pick it up and I'm going to move it over here. I can't change the direction of that arrow, right? It's like that. That's the direction of the arrow. I pick it up and I put it that way. So I draw it exactly the same, and this is force of tension 1. Okay. My force of tension 2 arrow is like that. So all I can do is pick it up and add it tip to tail. So I'm going to put it right there to add it tip to tail. So I want to make this easier for you guys because sign questions are a little bit trickier. So I will always make these so they work out to be 90 degrees. There's situations where it doesn't, but I won't make those situations. That's always going to be 90 degrees. And then my last arrow, which is FG, which is downwards like that, I'm going to pick it up and I'm going to put it tip to tail like that, and it goes straight down. So that is my triangle, and I get a nice right angle triangle there. Okay, the trickiest thing with this is the angles. People get weirded out by the angles, and the best angle to look at is right here. So FT2 goes up in this direction, and from the horizontal, it's 50 degrees from the horizontal. So this horizontal line here, right there, that's my horizontal line. It's 50 degrees from that line. So that means that if I draw on the same horizontal line here, because this is the same arrow, that this is going to be 50 degrees from that horizontal line, right? It's exactly the same. And if this is straight down, right, we know that this is 90 degrees, so this angle in here is 40 degrees. And that's the easiest way to find an angle in there. Okay. So I should label this FG as well. So the last question's asking, determine the tension in each wire. So to determine the tension in each wire, I need a side and I need an angle. So we already found an angle, but we need a side. So the easiest side to find is this side right here where FG equals mg, because our sine is 25 kilograms. G is 9.81 meters per second squared. So I can find my side by just going 25 times 9.81. Oops, and I get my answer 245.25 newtons. So now I have a side and an angle. I can use so, ka, toa to finish this off, right? I have this side, this is my hypotenuse side over here, so I want my adjacent side, which is FT2. So this would be adjacent and hypotenuse, so to find FT2 would be like that. So I have cos theta equals adjacent over hypotenuse. I want to find adjacent, so it's just going to be 245.25 newtons cos of 40 degrees. And then FT1 is going to be opposite hypotenuse, so it's going to be sine theta equals opposite over hypotenuse. I want to find opposite, so I move hypotenuse up there. So it's going to be 245.25 newtons, and it's going to be sine 40 degrees, like that. Okay, so this is FT2, and this is FT1. So I'll type both of those into my calculator. So FT2 is going to be 245.25, and it's going to be cos of 40. So that's FT2. And then 245.25 sine of 40, that's going to be FT1. Right? We have two sig digs, so you'd probably answer in scientific notation, but yeah, so 188 and 158 is fine, I guess. I should have put another sig dig on there. So we're going to finish off this lesson with a board question, and I want you to do this board question step by step. Most people aren't good at the first few steps, so I want you to take a few pauses along the way. So we're going to start this off with the free body diagram. So pause it, try your free body diagram, don't do anything else, and then come back and see if your free body diagram was actually right before you finish the question. Okay, so I'm going to draw the free body diagram now. So we have our physics sign here. Obviously we have a force of gravity here, which pretty much everyone's good at. And then most people are pretty good at this. There's a cable, so force of tension here in the cable. But some people stop there, so you might have stopped there and been like, yep, that's my free body diagram. But that's not correct, because what we want is we want a net force of 0 for any sign. So we have a force of tension in the y, and yeah, my force of tension in the y could cancel out with my force of gravity. But we also have a force of tension in the x. So nothing cancels that out, so that means my sign is going to accelerate to the left there. So we need something to cancel this out, and that's where that force applied by the pole there, or you could call it force of tension, but it's really force applied by the pole is, and that's our free body diagram. Right? If I go back to the original picture, if you picture this pole, if I take this pole and then I remove it, what my sign's going to do is my sign is going to go this way. So that means that my pole must be pushing that way. So that's why this is the correct free body diagram. So now that we've drawn the correct free body diagram, try doing a tip-to-tail vector addition showing the net force on the sign with the correct one. Okay, so pause the video here and I will do it. So we can't change the direction of it. So I'm going to start with this force of tension. And that's my force of tension. And then I'm going to do this force applied next. And then I'm going to do my force of gravity down like that. Right? So the reason that I want to do it, or actually that's not how I want to do it. So this is force of gravity. It's fine to do it that way, but we know that this is 50 degrees from the picture. From the force of tension to the wall, it's 50 degrees. So what we'd have to know is that that is 40 degrees, and that's fine to do. Or the other way that you could do it is if you did your force of tension first, like that, and then you did your force of gravity next, and then your force applied this way. Well, now this angle is 50 degrees. Both are correct, but if you draw it this way, then you don't need to think about it and be like, oh, what's that angle from? But both are correct. You could do it either way, so that's the correct tip to tail. And then the last part of this is determine the tension in the wire. So we want to find Ft. So pause the video, see if you can find FT. And we need a side, so I'm just going to use this diagram here. And mg is always FG, so we can just go 15 kilograms times 9.81 meters per second squared. So we have that side, right? And we would try to find this. So this is adjacent and hypotenuse. So I would use this. So cos theta equals adjacent over hypotenuse. And this time we're trying to find hypotenuse. So I'd move hypotenuse up and cos theta down below. So my adjacent side is at 15 times 9.81. And then cos 50 degrees. So if I type that into my calculator, on top I have 15 times 9.81 divided by cos of 50, and you end up getting 229 for it. So 229 newtons is your force of tension in that wire. Okay, that is all. Try these homework questions and let me know if you need help.